in this video we're going to do a quick review of the problems we went through in class. So for the first question, it says, how many sig figs are in 10,800? Well, if we go with our rules, we know that the 1 and the 8 are significant because those are non-zero digits. This 0 in the middle is significant because it's sandwiched between two numbers. Now the zeros to the right of the 8, because there isn't a decimal place, these would not count. Those are not significant. So in this case, there would be 3 significant figures. For the next question, it says round that number to 3 significant figures. So following our rules, any leading zeros, so numbers that are to the left of the first non-zero number, those wouldn't count. So this wouldn't count, this wouldn't count, this wouldn't count. Well, now we're at a non-zero number. So the 1 would count, and it's asking us to round to 3 sig figs. So I'm going to continue highlighting numbers that count until I've got 3. So here I have my first 3 significant numbers, and now I look at the 8. Do I round this to 101 or do I leave it at 100? Well, I would round this to 101, and I would end up like that. All right, the next question says, write the isotopic notation of oxygen 16 and oxygen 18, and then explain the difference between them. Well, we've got 18, we have 8 protons for each of these oxygen ions, or atoms, isotopes. It's Friday. All right, next we want oxygen 16 for one of them and oxygen 18 for the other. Okay, so these are isotopes of each other because they have the same number of protons but a different number of neutrons. So the difference between them would be different neutrons, different number of neutrons. Okay, so from the mass number, if we subtracted out the number of protons, this would have 8 neutrons. This would have 10 neutrons. All right. For this one here, it says calculate the average atomic mass and identify the element. Now in this problem here, it says we have a remainder. So the total abundance should add up to 100. So the first thing we need to do is we need to find out this remainder. So from 100%, I'm going to subtract 3.41, 20.91, and 25.16. And when I do that, so 100 minus 3.41 minus 20.91 minus 25.16, I get 50.52. Okay, now that I have this remainder here, I'm going to multiply each mass by its abundance. And I'm going to do this abundance in decimal form. Okay. So for the first one, for isotope number 1, we have a mass of 204. And I'm going to multiply that by the abundance in decimal form, which is 0.00341. For the second one, it's going to be 206 times 20.91. Oops, this needs to be in decimal form. 0.2091. For 207, it'll be 0.2516. And then finally, 208 times 0.5052. Okay. So when I go to multiply these out, bring in my calculator. First one, we've got 204 times 0.00341. That gives us 0.69564. For the second one here, 206 times 0.2091. That gives us 43.0746. 07 times 0.2516, 52.0812. And then finally, 208 times 0.5052. 105.0816. Okay. So next, I'm going to go ahead and add up all of these numbers. So my dog gets excited about chemistry. 0.69564 plus 43.0746 plus 52.0812 plus 105.0816. I get 200.93. All right, so now what I'm going to do is I'm going to go to the periodic table and I want to find which element has a mass of 200.93. So if I go to table.com, 200.93 should be mercury here. All right. Okay, what's different about these isotopes of uranium? Well, if you look at them, they all have the same number of protons, which is 92. Okay? However, they have a different number of mass number here. So, because they have a different mass number and the same number of protons, they're going to have a different number of neutrons. All right. Question says, which of these isotopes is most common? And then how do you know? On our periodic table, we have a atomic mass that's listed on here, okay, 238. And if you notice, one of our isotopes is 238. It's almost the same number. So because our atomic mass matches up so closely with this mass right here, that means that this isotope right here is the most abundant. So when we do our weighted average, this 238, uranium-238, there's the most of it. It's basically skewing our average towards 238 because there's so much of it. Okay, it's like your grade in school. If you did awesome on a test, all right, and it had a major impact on your grade, it's going to bring your grade up. But if you turn in like a homework assignment or you miss a homework assignment, it's not going to have very much effect on your grade because it's got a very small weight. Okay? It's worth a very small amount of the total amount of points of your grade. All right, why is this atom of helium unstable? So for elements 1 to 20, it is a 1-to-1 ratio of protons to neutrons. When we get to, I believe it's 82, anything 82 or above, they're always unstable. And then anything between that, it can follow a different rule. Okay, sometimes it's 1 to 2. So in this case, we have 2 protons, so it should be a 1-to-1 ratio of protons to neutrons. So we should have 2 neutrons, but we have 3. So that's why in this case, this helium ion is unstable. Which of the following is an isotope of lithium-6? So the 6 right here is the mass number. Lithium on the periodic table has 3 protons. So looking at our options here, this first one here has a mass number of 6, which is the same mass number that we have right here. So that's the same thing, basically. The second one also has a mass of 6, but I tried to trick you with this. Okay? Charge has nothing to do with isotopes. This last one here has a mass of 7. So that means that it has 4 neutrons, and in this case would be an isotope of lithium-6. So all of these have 3 protons, but lithium-6 and lithium-7 have a different number of neutrons. All right, let's look at this last one here. So this is from a mass spec. So on this example here, we put a sample into a mass spectrometer, and it gave us a readout. Okay? On this readout, we have a bunch of information, and what we need to do with this is we need to use that information to try and determine our average atomic mass. And then using that average atomic mass, we want to identify what we have here. All right. So the first thing we need to do is we need to pull some data off of the graph here. Okay, so we have our M over Z ratio. The M over Z ratio, I want you to think about that as your mass. And then the relative abundance, the intensity here, okay. So let's look at 10. So for 10, we have an intensity of about 12, and for 11, we have an intensity of 100. Okay. So we need to first find out our total. So we have an intensity of 12, and we have an intensity of 100. So let's add those numbers up. So 100 plus 12 gives us a total of 112. And then we're going to follow the same pattern that we did before. So we're going to take the mass, and we're going to multiply it by the intensity. So for 10, we're going to do its intensity, which is 12, over the total intensity, which is 112, and then multiply it by the mass. There's a lot going on here. So this is the part over the whole, and then this is the mass right here. Okay. So let's bring out our calculator again. So 12 divided by 112, and then I'm going to multiply that number by 10, and we get 1.07. And then I'm going to do the same thing with 11. So that was 100 over 112 times 11. So 100 divided by 112, not 122. And then let's multiply that by 11. So I got 9.82. And then let's add those numbers together. 9.82 plus 1.07. We get 10.89. And if we go to our handy dandy periodic table, 10.89 is closest to boron. So we would have boron in this case. All right, and those are the examples that we did in class, and that should get you prepped for the next test.